Hello everyone, my name is Yan and I am a MSCE student in Northwestern University. This is my first year here. So today I will talk about underwater object detection and multi-object tracking under domain shifts. This is a literature survey, but I don't want to make it too abstract, so I combine a case study which is made by myself today here. This is the brief contents I would like to share today. Motivation, core challenge, scope and differences from related topics, major tasks, comparison, and papers, case study, future directions, and conclusion. Underwater vision is important because many underwater applications depend on detecting and tracking objects. For example, underwater robots are used for inspection, marine observation, aquaculture, archaeology, and search and rescue. In these applications, the system needs to find objects in a scene and track them over time. For example, marine scientists track fish to study their behavior. Robots detect structures when inspecting pipelines or ships. So, detection and tracking are not just optional tools. They are basic tools that help us understand and measure the underwater environment. However, underwater vision is very difficult. The main reason is that underwater images are very different from images taken in the air. Light behaves differently in water. Different wavelengths disappear at different depths. Particles in water create backscatter, which adds noise to the image. Water turbidity also reduces contrast. Because of all of these factors, underwater images often have low contrast, strange colors, and unstable lighting. As a result, computer vision models trained in one environment often fail in another environment. This problem is called domain shift, and it is the central focus of the survey. So now let's talk about the core challenge of this problem. The central challenge is domain shift. This means that the data used for training and the data used during deployment are often very different. In underwater environments, scenes can vary a lot across different locations, water types, camera platforms, and visibility conditions. For example, water in the open ocean looks very different from water near the coast or in a tank. Another important issue is how light behaves underwater. Unlike in air, different wavelengths of light attenuate differently in water. As you can see in the figure, light attenuation changes depending on the type of water. In addition, underwater images are affected by backscatter, turbidity, weak contrast, refraction, motion blur, and unstable lighting. All of these factors reduce the reliability of visual features. Because of this, models that work well in one environment often fail when applied to another domain. Now, I will explain the scope of the survey and how it differs from related topics. This survey studies underwater vision from the perspective of domain shift. Instead of covering every possible underwater vision task, this survey focuses on three key parts of the perception pipeline. These are image enhancement, object detection, and multi-object tracking. First, image enhancement is treated as a supporting module. It is often used to improve image visibility before detection or tracking. Second, object detection focuses on locating objects in underwater scenes. Third, multi-object tracking tries to maintain object identities across frames. Another important point is that underwater perception is not simply a harder version of normal computer vision. In underwater environments, the physics of image formation is different. Light attenuation, scattering, and water conditions change how images are captured. Because of this, the key problem is not only image quality, but also how well models transfer across different environments. So the main issue becomes both visual degradation and cross-domain transfer. Next, I will briefly introduce the major tasks in this research area. In this survey, the topic can be divided into 4 main tasks. The first one is Task A, which is underwater image enhancement. Here, enhancement methods are treated as a supporting module to improve image visibility before detection or tracking. The second one is Task B, which is underwater object detection under domain shift. This focuses on detecting objects when the testing environment is different from the training environment. The third one is Task C, which is underwater multi-object tracking under domain shift. The goal here is to track multiple objects across frames while maintaining consistent identities. Finally, Task D focuses on datasets, metrics, and evaluation protocols. This part studies how we evaluate detection and tracking system and how we measure cross-domain robustness. In the following section, I will discuss each of these tasks in more detail. Now, let's look at Task A and Task B, which are image enhancement and object detection. First, Task A is underwater image enhancement. In many underwater vision systems, enhancement is used as pre-processing step to improve visibility and contrast. However, an important point in the paper is that enhancement should be treated as a support model, not the final goal. In other words, making an image look visually better does not always improve detection or tracking performance. Some enhancement methods may even introduce artifacts or artificial colors that confuse the detector. So, recent research compared to the past research focuses more on task-aware enhancement, where enhancement is optimized together with the detection task. And now let's move to Task B, underwater object detection under domain shift. Detection models often perform well when training and testing data come from the same environment. But when the testing environment changes, for example, different water types or lighting conditions, detection's performance often drops significantly. There are 2 main strategies to address this problem. The first one is domain adaptation, which uses information from the target domain during training. The second one is domain generalization, which aims to learn representations that work well even in unseen environments. In practice, domain generalization is closer to real-world robotic deployments because future environments are usually unknown. Now, let's move to Task C and Task D, which focus on tracking and evaluation. First, Task C is underwater multi-object tracking. Most modern tracking systems still follow the tracking by detection paradigm. This means the system first detects objects in each frame and then associates them across time. This approach is still a strong baseline. However, in underwater environments, tracking is often limited by unstable detections. If the detector misses objects or produces noisy bounding boxes, the tracking results quickly become fragmented. Another challenge is re-identification, or re-ID. Re-ID tries to recognize the same object across frames, but underwater environments make this difficult, because appearance features like color and texture are often weak and inconsistent. Now let's look at Task D, which is about datasets, metrics, and evaluation protocols. For object detection, common metrics include precision, recall, and MAP. For tracking, we also use metrics such as these. Another important point is that evaluation should include cross-domain robustness, not only within domain accuracy. In other words, we should measure how well a module transfers across different underwater environments. This figure shows how underwater tracking datasets have grown over time. Now, I will briefly summarize the comparison between several representative approaches. First, physics-based underwater image enhancement methods try to explicitly model the underwater image formation process. These methods are interpretable because they are based on physical models of light attenuation and scattering. However, they are often sensitive to assumptions, such as water type or scene depth. If these assumptions are incorrect, the results may degrade. Second, learning-based enhancement methods use deep neural networks to learn the mapping from degraded images to enhanced images. These methods are more flexible and can model complex visual transformation. However, they sometimes fail to preserve features that are important for downstream tasks like detection and tracking. Next, in terms of handling domain shifts, one approach is domain adaptation. Domain adaptation methods use information from the target domain during training, which helps align feature distributions between domains. However, this approach requires access to the target domain in advance. Another approach is domain generalization. Instead of adapting to a specific target domain, domain generalization tries to learn representations that work well on unseen environments. This is closer to real-world robotic deployment, but it is also more difficult to achieve in practice. First, the first figure shows example from the dataset. This dataset contains a very large number of underwater videos. It includes many different object categories such as fish, turtles, people, and underwater vehicles. The scenes are also very diverse. Some videos come from aquarism. Some come from open ocean environments, and others from controlled experiments. So this dataset mainly highlights category diversity and scene diversity. And for this figure, it is an example of a tracking model designed for datasets like the one we just saw. As shown in the previous figure, datasets such as these contain many different objects and very diverse underwater scenes. Because of this diversity, the tracking model needs to be robust to changes in appearance, lighting, and motion. This figure shows one representative approach. The key idea is to use a teacher-student training framework. So the above one is the teacher model, and the below one is student training framework. At the top of the diagram, the teacher model processes enhanced frames and learns from visual features of the target object. These features contain richer information about the object's appearance and structure, and this knowledge is transferred to the student model, which processes the original underwater frames. In this way, the student model learns more stable and reliable tracking features. Another important design is that the teacher model is only used during training. After training is finished, the system only uses the student model during inference, which keeps the model efficient. This design allows the tracker to benefit from strong guidance during training, while still remaining lightweight during deployment. Overall, this approach helps the tracking system handle complex underwater scenes like those we see before. Next, the second and third dataset come from another dataset. Compared with the one we have discussed before, this one focuses more on specific challenges in underwater tracking. For example, the images show situations with low visibility, where the water becomes blurry and foggy. There are also cases of camouflage, where the object color is very similar to the background. Another example is distractors. Where many similar objects appear in the same scene, the dataset also includes out-of-plane motion, where the object rotates or changes shape during movement. Finally, the third figure shows watercolor variation, where the same type of object appears under very different watercolor. As you can see in the list here, this is the different models for different datasets, and I listed its performance from the best to the worst. Since I don't want to make this literature survey to be too abstract, so I will briefly introduce a small case study based on what I have done before. The goal for this experiment is to build a simple prototype system for underwater detection and tracking. Let me first explain the left image. In this setup, I create a simple experiment in a water tank with clear water. I use the curved object to simulate the shape of the fish body. I do the 3D print to simulate the fish. To capture the motion and shape more clearly, I manually annotated 5 key points along the curve. These key points help represent the bending structure of the object, which is similar to how fish bodies deform during motion. However, I do think there exists a domain shift here. There is a gap between the rigid 3D type prototype to the soft fish. The bounding box showed detected object region in the in the left image, while the key point described its internal geometry. Now let's look at the right side, which shows tracking pipeline implemented in the code. I use YOLO V8 for the detection and strong shot for the tracking. I learned this from the paper. The system starts with input detections, which come from the object detector. When the pipeline extracts appearance features for re-identification, shown here as the re-ID module, at the same time, the system uses motion modeling and camera motion composition, which helps stabilize tracking when the camera moves. The tracking itself follows a tracking by detection framework, similar to strong shot. Motion prediction is handled using OC sort with a common filter, which predicts object position in the next frame. Finally, the system builds a cost matrix that combines motion and appearance information. A linear solver is then used to associate detections across frames and maintain object identities. This small experiment shows an important observation. When the detection boxes are stable, the tracking and motion estimation work reliably. However, when detection becomes unstable, the tracking performance quickly degrades. This observation is consistent with what many papers in the literature also report. As you can see in those pictures, the above one is my result. Since I only have a small dataset I built myself, which is about 600 pictures, it is a kind of small dataset. So the result here is nearly perfect. I got over 90% accuracy. The pictures below is the tracking system. I got the speed over time and acceleration over time, which means I got the real-time speed and acceleration. What's more, I want to show you guys a UI interface I've made. For the right side, it is the real-time pictures. And for the left side, it is the real-time velocity, position, and acceleration. Now, I will briefly talk about some possible future directions for this research area. First, one important direction is to extend the survey with more recent underwater studies. In recent years, new datasets and models have appeared, especially with the development of deep learning and large-scale visual models. Including these newer works could help us better understand how the field is evolving. Secondly, it may be useful to compare underwater vision with other challenging vision environments. For example, environments such as foggy weather, low light scenes, and autonomous driving also face similar visual degradation problems. By comparing these domains, we may gain new insights into how models handle domain shifts. Finally, the case study should be expanded with more diverse scenes and imaging conditions. In my current experience, the setup is relatively simple and uses clear water in a controlled environment. Future experiments could include different water types, lighting conditions, and camera viewpoints. This would help evaluate whether the proposed ideas remain reliable under more realistic underwater conditions.